In this video, I will be examining iodine absorption. And so iodine, which I think is sort of most famously known to be needed for thyroid hormones, is absorbed in the intestine. But what we actually see here is that the iodine actually is secreted in saliva and in the stomach. Then it's in the intestine where it is taken back up. But we're going to be mostly interested here in the absorption of iodine. So here I just have kind of a key for understanding kind of this busy diagram here. So this SCN is thiocyanate, which is a pseudohalide. So it behaves similar to iodine in this case. And so it's a competitive inhibitor of this NIS, where the NIS is one of the two transporters I'm going to be looking at in more detail here. And so that is the sodium-iodide symporter. So it takes sodium and iodine in from the intestine. So we can see that right here. So these this thiocyanate can act as an inhibitor of that. And this SCNO, which we can see in some of these images here, is just SCN after it has reacted with oxygen. And so the other uh, tr transporter that I'll be looking at in more detail is this CFTR, which is the cystic fibrosis transmembrane conductance regulator, where cystic fibrosis is probably just a naming convention because it was probably discovered to be important in cystic fibrosis, but here it will not. We will not be talking about it in that context. And so we see the CFTR here, which is actually pumping iodine out in the saliva and in the stomach. But we see over here that it in the intestine, it seems to be kind of going in both directions. So they have this double arrow here for the CFTR activity in the intestine, which is where we are going to be interested in here. All right, so we'll first look at this sodium iodine symporter, and so we can see the active site here where, well, this is a structural alignment, so that right there, the purple sphere is the iodine. The sort of tetrahedral structure is this rhenium oxide, which kind of behaves similarly to iodide, which is kind of a large atom there. And the paper that I got these images from was very new, so I don't think it had even been published yet. It was on one of those archive websites, and so there wasn't actually a PDB structure of it available on the protein data bank, and so I wasn't able to obtain that to look at in PyMol. So we see the close-up of the structural alignment of the apo NIS, which is just with nothing bound, the iodide bound, in the rhenium oxide bound there. So the B is the tunnel calculated for the apo-NIS structure that connects the substrate binding pocket with the cytosol. And so we can see that here. So this is saying that the iodide, which is right there, will sort of move through this black mesh here into the cytosol. And so that is, remember, this is NIS here in the intestinal context. And so that is taking it from the lumen into the cell, so into the cytosol. And so they are saying that that is the path in which the iodide will take through the protein into the cytosol. So this is looking at that path here, looking at the rhenium oxide moving through that path right there. And so this is their proposed mechanism right here. So we have the iodide coming in and binding here. So we have these sodiums in it as well. So that's what the yellow are, what the yellow is. And so we undergo these conformational changes here. So going from here to here, we undergo these conformational changes, and now this iodide can sort of move out through there. And so we see that it's sort of moving through that tunnel that they propose, and so that it is then sort of exiting out of there. Then we have the conformation changing back to the apo state here so that it can take up more sodium and iodide. And so this is looking at the kinetics of this. So they were trying to show in this paper, and this is from a different paper, I believe, right here. And so they were looking at the kinetics of this, and they wanted to show that the, well, they show that the sodium here is, well, they knew that that was necessary. What they wanted to show in this paper is that this NIS is actually expressed on the apical surface of the enterocytes. And so they were looking at expression of these proteins on the apical surface of the enterocyte. And so what they see here is that well, this is looking at with this ClO4, so this perchlorate inhibitor with the iodide, and then with the iodide alone. So that seems to be inhibiting that. But down here is what I found interesting too. So, so feeding these mice with iodine enriched water, I believe. Yeah, so the rats were divided into 4 groups. They were treated with this 0.05% potassium iodide in the drinking water for 12, 24, or 48 hours. And so this is just showing that we have this down regulation of the NIS transporter when the rats are fed the iodine over time. And so the being exposed to iodine for greater and greater time is essentially down regulating the NIS, the sodium iodide transporter. But yeah, so this is just showing essentially that this is actually true, that this NIS here is actually expressed on the apical surface of the enterocytes in the intestine, and that the exposure to iodine for longer periods of time causes a down regulation of that sodium iodine transporter. And so over here we can look at the CFTR, so that's that cystic fibrosis transmembrane conductance regulator, which remember in the context of the intestine seems to have this sort of dual in and out movement of iodine, so it seems to be sort of controlling the equilibrium of the iodine in the enterocyte in the intestine. And so this has these two sort of subunits here. So this one and this one, with the transmembrane domains and the nucleotide binding domain. So this is actually an ATP regulated protein here. And so in this paper they were looking at this R domain, which is like a regulatory domain, which actually can be phosphorylated, and that causes it to move out of the way and allows for transport of the ions through it. And so this is actually looking at that. So they add the ATP here, and we see that the activity is pretty small until they add this protein kinase A here, which then causes the activity to begin right there. And so they're saying that there is this movement of the regulatory, this R domain, which is this sort of red tongue looking thing here. So that can move out of the way, which is sort of a rate limiting step. Then we have the protein kinase A, which kind of phosphorylates that and causes it to sort of stay out of the way, and allows the ions to then move through. And so this here was actually looking at the movement of ions, and so that's why it's looking at these picoamps here. And so once again, they add the ATP. There's very little activity until they actually add the protein kinase A. Then we see that we actually have this movement of charge going through there. And so then looking at this, we see that the ATP concentration, so looking at this ATP concentration, if we have the phosphorylated and the dephosphorylated regulatory domain, that the dephosphorylated has a much smaller activity here. And so this does seem to show that this phosphorylated regulatory domain is in fact what's allowing the charged particles, the ions, to move through this transporter. And so I actually have the structure here. And so in magenta here is our transporter. This little blue section here is that R domain, and then these gray residues are sort of where the R domain is interacting with the transporter. And so this is with the R domain here sort of in that state of being sort of inside the transporter here. So in the inhibited state right there, but we can remove that and put this in here, and so this is in the uninhibited state. And so we see this red ribbon right here is actually that R domain that's sort of moved out of the transporter. And so we can zoom in here, and these in this purple color here are those same residues that we saw here in gray that interact with that R domain. And so we can see that those have moved out of the way there. And so that will actually allow the ions to move through that transporter there. But yeah, anyway, those were the two transporters I wanted to look at in this. Once again, the sort of take-home message here is this NIS, this sodium-iodide transporter, is moving iodide into the cell here, and I'm specifically, I keep saying iodide because these are reduced. So the iodate and other iodide forms are reduced to the iodide ion there. So yeah, these are just a couple of the transporters that are kind of the major players in this iodide import or absorption from the intestine, where this NIS, this sodium iodide transporter, is sort of the major player going on here. But anyway, I hope you found this video interesting, and I will see you in the next one.